Page attention similar to
Someone check
page attention similar to page.
Are we?
Nakita last slides tintuntada version.
Yeah.
Yeah, we are.
Right.
I'm asking.
I think we need to mute the other guy. Please mute it.
Thank you.
Mute the speaker and the microphone. All right, guys. So welcome to the second lecture of student talks. Last time it was really amazing. I enjoyed both of the talks. I got different opinion from you. So let's see who's the winner. And we will repeat the exact same thing also today. So you're going to vote for the best presentation, right? So make sure you do that toward the end. Don't do it now. Today we'll start with another two papers. Hopefully they will be interesting. So welcome to those watching us on YouTube live stream. If you have any question, please feel free to post it in the chat. For you, we will start the discussion toward the end of the presentation, all right? So yeah, you can start whenever you're ready.
First of all, good evening, everyone. So myself, Yasaswini, here are teammates.
Jagruthi.
So today we are here to present our paper presentation on RAIDR, Retention Aware Intelligent DRAM Refresh. So firstly, this is not me that we can see. So she's a girl. By seeing the picture itself, we can see that she's worried. So it's like the location is in a plant nursery. She's stuck with the watering the plants. So let me tell about the scenario. So she's like fed up, exhausted by watering the plants each and every day, because she's watering each and every plant and each and every day. So it is taking a lot more of water and a lot more of time and efforts. So she wanted to find a better way that could help her in the efforts wise and also in saving the water wise. So on the either ways. So obviously we humans, whenever we have a problem, will some or the other way come up with a solution. So here she is happy. So she found a solution where we can see in the picture itself, she just segregated the plants into fast drying plants and slow drying plants. So this would be a better idea, so that for the fast drying plants, she can water frequently and compared to the slow drying plants. And she wanted to tell the more about the ideology and more about the process she followed. She followed log books, where instead of just going to a plant and guessing it out, she had just recorded in a log book like which plant goes under which category. So this is how she achieved her dream. She had segregated everything perfectly, and the plants obtained or the plants also got ensured with correct amount of watering, and also that helped her efforts too. So from this scenario, let's relate to our paper, that is RAIDR, Retention Aware Intelligent DRAM Refresh. So before going into it, do you guys want to say anything or tell about DRAM? Like, what do you get or what do you remember when you think about DRAM, refresh or DRAM? Yeah, you do. I accept the full form too. I just need the interaction, so full form is also accepted. Excess memory. Thank you, guys. So let me relate the scenario to our paper. So firstly, she was wondering about the watering of plants every single day. So in the same way, DRAM cells need to be refreshed every single time in order to not lose the charge, that is not to lose the data. So in order to not lose that, DRAM memories must be refreshed continuously. And not all DRAM cells require the same time or same retention time to refresh, right? So like plants, like some plants need frequent watering and some do not. In the same way, DRAM cells to some require frequent refreshing in order to keep up with the data, and some do not. And as she segregated them into fast drying plants and slow drying plants, we are doing the same in this paper by just segregating our DRAM cells based upon the retention time. Here the plants, we are taking the factor of the drying factor, like how much water it needs, and here we are taking the time factor. If there's a row of bits, we are just taking the constraint of retention time, where we are just seeing like the entire row where up to which time it can hold the data. It's not like if one plant which needs less water dies, it doesn't mean all the plants dies. So in the same way, all the DRAM cells does not require the same refresh rate. So we segregate them based upon the retention time. And as she used the logbooks, we'll be using Bloom filters to do that, and we'll be diving deeper into that in the next slides. And finally, we'll be achieving that in the same way. The DRAM refresh rates are being reduced, with the decrease in the refresh rate, the system performance and energy efficiency also increases. So that's the reason. So this is all about the scenario mapping of our paper to the related situation or scenario. And now let's talk about the problem and goal. So as I mentioned before, the DRAM cells must be periodically refreshed to prevent the loss of data. And all DRAM cells do not require the refresh rate at the same frequency. Some require more frequent refreshing and some do not. And our goal is to minimize the number of refresh operations that to be performed without significantly increasing the hardware or software complexity, without modifications to the DRAM chips. Our aim is to find a minimum, our goal is to reach the minimum number of refresh operations, which is cost effective and also easier. And our paper proposes RAIDR, that is retention aware DRAM refresh, which is a low cost mechanism that can identify and skip unnecessary refreshes using the knowledge. As I mentioned, the constraint is retention times. Continuing that, I wanted to add some more about the summary of the paper. So this report investigates how DRAM refresh mechanisms affects the energy efficiency and performance, and explores the RAIDR technique as a potential solution. So in modern memory systems, DRAM cells must, as mentioned before, in modern memory systems, DRAMs must be refreshed periodically, which consumes significant energy and reduces system performance. The RAIDR mechanism obviously optimizes this problem by minimizing the refresh operations by grouping the DRAM cells into retention bins. And this is done using Bloom filters, allowing different refresh rates based on cell leakage characteristics. And RAIDR achieves 74.6% of refresh reduction, 16.1% of power reduction, and 8.6% of system performance improvement on an 8-core system with 32 GB RAM. So coming to the background and motivation, I wanted to discuss about, firstly, before getting into RAIDR, I want to discuss about DRAM, DRAM system organization, DRAM refresh, and DRAM retention time distribution, which helps us to get better understanding about how RAIDR helps in all this. So firstly, DRAM. So DRAM is like composed of dynamic random access memory cells, where each cell stores charge on the capacitor. So each cell has a capacitor and transistor, and our charge or data is stored on the capacitor. And this charge leaks causes the data loss. In order to stop the data loss or leak of the charge, we do refreshing. And what is refreshing mean? We are like pointing to refreshing multiple times. So refreshing is nothing but the data is stored in DRAM, right? So in order to refresh it, we will be reading out and reading and rewritten of the data, refreshes and helps in not losing the data. And coming to the DRAM system organization, so the memory controller is linked to channels. It can have one or more channels, and each channel has one or more ranks, and each rank has one or more banks. The hierarchy is over there. So channel can have one or more ranks, and rank can have one or more banks. So what is a channel? Channel is the highest level of hierarchy, and it has commands, address, and databases. And this channel is the communication between memory controller and to the ranks. And ranks are the set of independent DRAM devices that operates parallelly, and banks are distinct DRAM cell array 2D and can operate parallelly. So to understand that in a better way, so the basic level would be bank, and each bank would be having a row decoder and row buffer. Where row decoder will have the DRAM cells connected, and row buffer is an array of sense amplifiers. So this is word line, and this is bit line. So first let's see how what is bit line, what is word line, and how does the access to data happens in DRAM. So firstly, coming to the bit lines, these bit lines connect the DRAM cells to rest of the system. So this bit lines helps and user to read and write the data. And coming to the word line controls the bit lines and also uses for accessing data. And to see how this works, so each cell has capacitor and access transistor. So when the word line activates, it passes the command to the access transistor, which gives permission to the bit line. Sorry. And this access transistor gives the permission to the bit line to communicate with the capacitor. And as we know and known before, that the bit line helps our user to read and write. That's how the bit line communicates with the capacitor and the operations happen. And that is the diagram. and that flow of work has been mentioned over there. So to access data in DRAM, we must open the row containing the data to place it on the bit line. In order to open the row, bit lines must be charged to supply voltage by 2, half of the supply voltage. And then the rows word line is enabled, and which is connected to the capacitor of the all rows through the transistor. This causes charge to flow from capacitors to bit lines. That makes the read and write access options done. So next, coming to the DRAM refresh, the memory controller issues, and so we didn't get into the RAIDR yet. So coming to the baseline model, so the memory controller issues an auto refresh and chooses rows to refresh using an internal counter, which refreshes based upon the capacity. And the capacity of DRAM is number of rows in the device multiplied with the number of bits per row. And at normal temperature, average time for refresh is 7.8 microseconds. And at extended temperature, it is 3.9 microseconds, occupying all banks and preventing ranks to serve requests. So whenever a request comes to the cell, if a refresh operation is happening, then the access request need to wait. So it is all about that. So at extended temperature, if the retention time is 3.9 microseconds, then the refreshing is happening for every 3.9 microseconds. Where the refreshing is more, with the increase in refreshing rate, it stops to serve the other requests that come along. And this refresh operations degrade performance in following ways: loss of bank level parallelism. So when the banks are busy in doing refreshing, it could not satisfy or just take the access request it gets other than refreshing. And next one is increased memory access latency. That is nothing but access to any bank in refresh must wait for refresh latency. When a request comes, when the refresh is happening, it needs to wait until the refresh is done and the charge had been refreshed. So that time is called refresh latency, which is in order of 300 nanoseconds. And also coming about the DRAM refresh graphs, we can see in the first graph, we have the device capacity on the x-axis and auto refresh command latency on the y-axis. As I mentioned, the auto refresh command latency is nothing but the time it waits for the access request to get in till the refresh is done. So that has been continuously increasing, which at a point which is greater than 1000 nanoseconds. And in the second graph, in the throughput loss, you can see the throughput loss is nearly 50% for 64 GB. So throughput loss is nothing but the time the refresh takes divided by the time it needs to wait for the refresh. And coming to the DRAM retention time, so we have the refresh interval on the x-axis and cumulative cell failure probability on the y-axis. So less than 1000 cell failures, less than 1000 cells needs less than 256 milliseconds retention time. But in the baseline model, we'll be doing for every 64 milliseconds. It is like nearly 4 times, but literally less than 1000 cells required that sort of retention time, but we are doing the same rate for everything. And the other graphs tells about like only less than 30 cells need less than 128 milliseconds of retention time, and less than 1000 cells needs less than 256 milliseconds of retention time. And coming to the novelty, I want to discuss about the previous work which attacked these problems caused by DRAM refresh from both hardware and software angles. And some researchers have suggested changing the hardware inside the DRAM chips so that the memory cells can hold the data better, and that may help with the refresh rates. but the extra hardware takes up to 5 to 20% of more space on the chip, which makes the chips more bigger and expensive. So our paper RAIDR has a low cost mechanism, achieving 74.6% of refresh reduction, 16.1% of power reduction, and 8.6% of system performance improvement.
So by now you already understood the basic terms like DRAM, what is DRAM refresh, and what is the problem we are facing. And in the next coming slides, you are going to see how we are going to solve and how RAIDR is going to solve the DRAM refresh issues. So RAIDR is nothing but retention aware intelligent DRAM refresh. So it has mainly 3 steps. In the starting of the slides, my teammate has explained a scenario, which is a plant scenario. So we can relate these 3 points to that scenario, which is nothing but first step is profiling, and the second one is storing rows into bins by retention time, which is nothing but binning, and the third one is refreshes issued when necessary. So the first step we can relate to she's checking like whether which plant belongs to wet she's checking like whether it belongs to the wet plants or the dry plants. So we can consider the profiling step like that. And in the second scenario, she's grouping them, like binning is nothing but the grouping section. So she's separating them to dry plants and wet plants. And the third thing she's doing the watering section. So for some plants she's watering every day, and for some plants she's watering like 3 days once or weekly once, something like that. So we can relate that situation to these 3 points, and we will go deeper into the 3 steps, and we will understand like how this RAIDR is going to solve the issue. We'll go deep into the first step, profiling the retention time of all rows. By this heading only, you can understand we are going to calculate retention time of all rows, and we are going to store them. So the first step is nothing but write all zeros or ones into the row. We can think of a situation like we have different sizes of cups in our hands, and we want to fill the water in it. So the smaller cups takes less time, and the larger ones take a lot more time than the smaller ones. So we are going to observe the time which is taking like to fill those cups, and we are going to record that time, and we are going to use that time in the coming future, maybe to fill those cups again. Like we can keep the cup there and we can go and call, and after 5 seconds, like we have already recorded the timing, and we can come back and we can stop the tap. So something like that we can relate to this one. So the first thing is we are taking all empty cups, write all zeros into the row. This is how we are going to write the zeros into the bit array. And the second one is don't refresh, and we are not going to switch off those tabs until they fill and they are going to leak. So the second step we can relate to that. And the third one is observe the first bit change, like the first one which cup is going to leak, we can observe that one. So in this image you can see after 128 milliseconds the fifth bit is going to change from 0 to 1. So here we can understand for this row address, after 128 milliseconds, like maybe at 128 milliseconds or less than 128 milliseconds, it is going to leak the charge. So this is how we are going to like note it down the retention times of those rows. So this is the step 1, which is nothing but the profiling part. We are going to calculate the retention times and we are going to store them. And in the second step, so you might wonder like we have already stored the retention times, like how they are going to be useful in the next steps. So the second step is nothing but storing DRAM rows into the bins. The memory controller stores each row into one bin based on their profile retention time, which we calculated in the first step. So for that, like to store all these rows into one bin, we are going to use the Bloom filters. Bloom filter going to will go to the bin and going to search for that particular row's address. And if it is available, it says the address is already available in the bin. You can go and refresh. And if it is not available, it says it's not available and you don't need to refresh that particular row. So we have like 3 different kinds of bins here. Like we can consider one is like a short one, medium one, or the large one. Yeah, the Bloom filter is like a data structure which is used to determine if an element is part of a set or not. Then it has like a bit array and some hash functions as well, like to store. These hash functions are used to store those bits calculated from the hash functions into the bin. And the bit array is to flip the bits from 0 to 1. So this is how we have already calculated the retention time in the first step. In the second step, we are going to put them in the bins. For example, if you here see 64 milliseconds is the one bin and 64 milliseconds to 128 is the second bin and 128 milliseconds to 256 is the third bin. It's around 128 milliseconds in the example we calculated. So we are already putting that into the 64 milliseconds to 128 milliseconds bin. So this is how the second step is going to work. So now we'll go and understand the scenarios in this, whether this, if the particular element is available in the bin, then what will happen, like how the Bloom filter is going to search for that, and what are the scenarios we have in that. So let me ask a question now. So you understand Bloom filter is a data structure. You might have already got a question, why only Bloom filter? Why not other data structures? You are already a computer science student, so you might know data structures. You can answer it. You can try at least. We have donuts here waiting from so long. Yeah. Yeah, you're close. Almost. Like, what are the different types of data structures we have for searching, if I mention it more precisely?
Yeah, please, everyone, close screens. Any kind of screen, close it.
Yeah, graph, linear search, binary search, all these are like will take like a lot more time. Linear search means like searching one by one, and binary search means it needs a sorted array. So all these are costly and it will take so much of time. So that is why we the RAIDR, like the authors have selected Bloom filters for this searching part. So now we'll go into the example. We are considering here in the paper itself, the authors has considered 64 to 128 milliseconds bin with 3 hash functions over a 16-bit array. So the first thing we need to do is the initialize the bit array to 0. So we are going to initialize all the bits, like we have considered 16-bit one. So all the bits we are considering it to 0, and we have considered 3 hash functions here. And second step is going to insert some of the address, like one address we can insert into the bin that we are calling as X. And this is how, like, we'll pass that address X into the hash functions, 3 hash functions. Those will give you some bits, like some indexes, those will give. So for example, here in this example, you can see that the hash function 1 already gave us like index 1 and 5 and 7. So that's why we have turned all the zeros in those indexes from zeros to 1. This is how the first like insertion happens into the bin. So the next thing, we are going to test it. Like when a DRAM cell has to refresh, we are going to test this address X, and we are going to check in the bin. We will take that row address X, and we are going to give it to the hash functions again for testing, and they will give the bit indexes. So we will give those bit indexes to the Bloom filter. Bloom filter will go into the bin, and it is going to check whether all the bits which has given, like hash functions given, are ones or zeros. Whether if any of them are zeros, then the Bloom filter will say this row is not at all available in the bin. We need to insert it, and we need to turn them into the turn from zeros to 1. So here in this example, the hash functions already gave 1 1 1. So the Bloom filter is already saying the row address X is already available in the bin. And we'll see one more example. We'll test for address Z that we haven't already placed in the bin. The hash functions gave like 1 0 1 as the hash functions output, and we are going to check those addresses, those bit indexes in the bin, and it is like 1 0 1. Those bits are, so our Bloom filter is going to say it's not at all present. We need to insert it and we need to refresh it, and that is what the Bloom filter identifies. And we have one more scenario as well, which is like false positive scenarios. So we have if the address W, if we consider, we are not inserting that into the bin, but still the hash function is giving, by any chance, like by chance, if it is giving the same addresses, something like X, we can consider they are already available and they were turned from zeros to 1. So what our Bloom filter says, it is already present, then it is getting refreshed. False positive means the address X is not at all inserted into the bin, but still because of some other rows it's already showing like it is present. But so now because if we have already the address W inside the bin, so our radar goes to starts refreshing that DRAM cell, which does not affect any of the like performance or energy, and it doesn't waste any time, because like we have multiples of DRAM cells. So refreshing one cell does not affect like large amount of percentage of the performance.
Yeah. So let's go with the step 3, which is an intelligent refresh. So let's ask some about this to the students here. So does anyone have any idea on the intelligent refresh? So by the name, what do you think? Any answers? Sorry? Yes, correct. Exactly. Yeah. Really great answer. So yeah. So here, let's connect with the Yasaswini's story introduction. So here, he's think of like a smart gardener. So here, he is pouring the water when it is being needed. Not so each different plant has a different rates of water level and the time. So he only feeds water when it is required and what amount of water level it is required for a particular plant. So it's the same like an intelligent refresh. It effectively refreshes only when its retention time bin expires. So, and here comes an important thing, that is row counter. You usually know about the row counter is, so it will go to the every row and refreshes for every 64 milliseconds. And a period counter also plays an important role in the intelligent refresh. It tracks how many 64 milliseconds cycles has been passed. So it will take a note of, okay, once it is being refreshed, it will take a note. Okay, this is the 64 milliseconds time it has been tracked. So this is how the period counter plays an important role. So let's see how each row, how it will be calculated for in each row. So it will check the retention bin via Bloom filter. So Bloom filter, you already know that, like when arrow has its, if an element has been present in that, I mean, if a row is been present to the retention bin, it will check, right? And then it will compare with the current period counter. So since it is already tracking how many 64 milliseconds has been refreshed, so it will calculate, compare the current period counter to the bin's refresh. And then if the interval is being expired, it will refresh. If it is not, it will just skip that level. And this process will be continuously repeated for every row at a proper rate. So let's have an overview of the refreshing the rows. Like so here, each row is being selected for every 64 seconds, and this row is being selected by row counter. So it selects rows with the row counter, and then it will check like if this is being belongs to whether the row is in 64 to 128 bin, or if it is yes, so then it will refresh that row. If it is not, it will keep on checking like whether it is been present in 128 to 256 pin retention time. So if it is yes, it will refresh for the every second of 64 milliseconds. Here we are taking the refreshing base interval time as a power of 2, which is a multiple of 64. And since if it is no, it will refresh the row for every fourth 64 milliseconds. So this is overview of the refreshing, refreshing the rows. And let's know about how the selection of rows will be done with the row counter. So here are the 4 main steps for the selection of the rows with the row counter. And first is the row counter functionality. So here the row counter sequentially, it's placed like an iterator and checks the DRAM for every 64 milliseconds. You may have a doubt like why they are considering only 64 milliseconds, like they can also consider as 0 to 50 seconds or maybe 75 seconds, right? But this base interval refresh is being defined by JD EC. They have done extensive research and practical hands-on experience, and they have defined 64 millisecond as a base refresh interval. And this is how this ensures the full coverage, missing of no data loss, and every row is being checked within that base interval. And then the counter will increment, like the period counter will increments once it wraps around when it reaches the final row. Okay, then Bloom filter will come up into the picture. Like it calculates, we all know that it has as you can see here, for an example, bin 1 will have 0 to 64 seconds, and bin 2 is having 64 to 128 milliseconds, and bin 3 he will have 128 to 256 milliseconds, right? So this membership test will be storing by the Bloom filter. So and this lookup will tell which row it is been belonging to the which. I mean, for an example, if a row is being selected like 100th row, the Bloom filter will tell, okay, this 100th row is been belongs to this bin, like bin 2, bin 3, bin 1. So this is. And next, we will go with the decision logic. So once we have identified the bin, the controller will counts the period counter, and check if the bin has been expired. So if the bin is not expired, it will just skip it. If it is being expired, it will refresh the row. And Bloom filter may give you the false positive, but it will causes only the extra refreshes, but it doesn't make any risk to the missed ones or the data loss. And the fourth one is refresh scheduling. So it will schedule based on the selective, like it will select only a subset of the rows that is being refreshed for each pass. And over the multiples of 64 milliseconds of the cycles, only the slow builds is being refreshed every 256 milliseconds. And yeah, the refresh order is being fixed, so there is no refresh frequency is being adaptive. So this is how the selection of the rows with the row counter happens. So yeah, so as you can see in this picture, we have a main memory controller and the addresses. And there are two banks, bank 1 and bank 2, and here is we have a row counter. So first, initially it will check at the first row of the bank 1, and then the first row of the bank 2, and the second row of the bank 1, and the second row of the bank 2. This is how the row counter will select the memory addresses in the addresses in the main memory. Okay, so overview of the selection of the rows with the row counter. So here the radars only refreshes like like he answered. It only refreshes when it is being needed. If it's been says it's due, then only it refreshes the row. And yeah, here as I said, row counter acts as an iterator. So it will think like which row I need to go next. So this is how it went. And the Bloom filter plays a major role, whether which it will tell which row belongs to that bin, like if a row is bin belongs to which bin. And then, yeah, you may get doubt like how this retention time is being calculated since the last refresh, right? So let's go with that. Here, as we already know that row counter and period counter has been plays a major role. So it will go every DRAM row, it will refresh for every 64 milliseconds. And then the period counter increments every time when the row counter resets. So so let's see, let's have an example to know more better how the time is being determined since the last refresh. So let's say bin 0, bin 1 and bin 2 is, and the retention interval is from 0 to 64 and 128 and 256. And for an example, arrow belongs to the bin 2, like arrow has been belonging to the bin 2, bin 2. And then initially at the 0 milliseconds, row counter starts as 0. I mean, it will take the value of 0, and the period counter is as 0, and because there is no refresh happen, so the row is being refreshed because it's the first one. So since now if it is being refreshed, if and at what time it will stop, so that's the time interval they will calculate, right? So initially the row will be refreshed, and step 2 at the 64. So we know that the base interval is from 0 to 64, right? So at the 64 milliseconds, the row counter finishes the full round, and the period counter will, since it has been completed the full round, the period counter will be incremented by 1. And since it has been past 64 milliseconds, so the period counter, okay. So if the period counter value is 1, that means that it has a refresh of 64 milliseconds. And the row is not matching with the bin 2, so that's it will go on with the next step, which is 128. And the period counter will becomes 2 because it will complete the second full round, since, and the period counter will becomes 2, and it will store 128 milliseconds has its past refresh, and the row is still not due because it doesn't reaches the bin 2, right? So, and you may got doubt why this 192 milliseconds has came. So we are taking 122 milliseconds as an example, which belongs to the bin 2 of 256. So here, since the time interval, the row time interval is taking as 192, the period counter becomes 3, and the 192 seconds has been passed. Since it is reached one full round, it is taken as 192 as last refresh, and the row will be still safe and does not refresh yet. And this is how the keep on checking about the time refresh. So this is how the retention time will be calculated since the last refresh. So here is a tabular form. As you can see, at the 0 the row counter is 0, and the period counter is row, and initially we are refreshing the row, so it is yes, and the time is 0, and 64 milliseconds it will complete for one loop. So the period counter will be 1, and there is no row refresh because since it is not reaching the bin timing. So this is how the time since last refresh is 128, and 192 since it is completing one row, the period counter will be 3, and then the row refreshing is not yet done, so 192, and at the 256 row the period counter will become 0, as you can see here. So here 192 milliseconds as an example, right? So here it belongs to 56 milliseconds. So here since it's been the base interval time is 64, right? So it will calculate as 0. So the period counter values from 0 to 3, and the values are 0, 1, 2, 3. So this is how it will calculate the period counter values. And let's see, yeah, so every mechanism will have a disadvantages or cons. So let's see what are the issues we can face in the DRAM and by using RAIDR. So this is how the high temperature issues in the DRAM. So here, whenever there is a high temperature, the DRAM will cells will shrink, and this will make the cells charge faster, and it will also shrink the shortest retention time because we have to refresh more frequently, right? So this decreases the retention time. which leads to the power consumption and low refresh overheads, and this also leads to reduce the memory performance as well. And let's see how this radar proposes a solution for the temperature effect. So temperature radar will uses a temperature dependent aware refresh bending, since that is the reason why it is been effectively resulted with a 75% of refresh reduction rate. And it will adjust the interval dynamically. For an example, if it is if it is at the extreme high temperature, it will adjust the base intervals from 32, 64 and 128, and without avoiding the data loss. And it will also increases the more refresh reduction rate. So, and then refreshes only when a robin says if it is due, and this will saves the power, energy and the performance as well, even if the heat stressed. And let's go with the evaluated methodology. So here they have used, the radar has used x86 simulator with cycle by cycle in the DRAM timing model. And the simulator, the DRAM has been validated against the DRAM Sim2 for accuracy. Like they want to test the CPU memory performance and everything, whether it is been acting same like a DRAM. That's the reason why they have used DRAM Sim2. And then they have used a pin as a tool to collect the memory, whether it's been performing same as the actual DRAM. And so DRAM, they have considered DDR3 datasheet as a micron as a power parameter. And here we can say that they have scaled the temperature from 32 to 256. And here are the benchmarks when you can so they have considered the workloads from spec CPU 2006. So they have tested to test the whether it's been consuming CPU memory controlling and everything. So, and TBCC, this has been used to the database reduction, and TBCH, this is used to know with the decision making analytics support. And they have considered the workload mixes from 0 to 25 then, and they have simulated 1 milliseconds at 64. It's approximately equal to 1000 milliseconds, which is equals to 256 milliseconds wall clock time at 400 gigahertz. And here, and you can see the evaluated system configuration. So they have given the range as 64 to 128, and they have using usually we I will ask one more question. So what type of DRAM we have used? I mean, what's the storage and what's the core we have used Yasaswini and Sunanda has stressed many times about this. So any answers for this? What amount of storage and the core we are testing against the DRAM? Yes. 64? No. 64 is not. Yeah, 32. Yeah, correct. Yes. So as you can see here, for the retention range of 64 to 128 milliseconds, the bloom filter size is 256, which is very less than the DRAM size. And so here they have considered 128 milliseconds to 256 milliseconds as 1 KB, which is very far less than 32 KB. And they have differentiated the number of entities evenly to ensure the error probability very less. So 10 and 6, and 64 to 128 range, the rows are 28. And so as you can see, 28 is very less number. So that means that we don't need to we can only require to refresh only 28 bins, which are in the range of 64 milliseconds to 128. And 976, the number that means that there are more stronger cells. That means there is no data loss, which doesn't require more frequent refreshes. And as you can see, the fall positive is very less for both retention ranges, bin 1 and bin 0. And so let's see like what are the other mechanisms they have considered against the radar. And so baseline auto refresh. So it's match with the introduction what we have. It will only plant every hour during the rain. And distributed refresh, this watering will happen one by one instead of all at once. And smart refresh, it will remember what you have watered recently and skip them. And the self refresher mode, which is an auto sprinkler that only that still waters everything equally. And the radar one, which is the smart gardener, which knows which plant water needs and only waters when it is needed. That saves time and energy and water. So let's see here. As you can see in the picture, they have considered the normal temperature and the extended temperature. And the normal temperature ranges from 55 to 65, and the extended temperature is from 85 to 95. And the base intervals, if the temperature is being increases, we will decrease the refresh interval time as 32, and the normal temperature, the base interval is 64. And here in the normal temperature and the extended temperature, the radar performs very great and reduces the 74 almost 75 percentage. So when compared to the performance analysis, here they are considered the memory intensive bench workloads as 0, 25, 50, 75, and 108 average. So if you can observe the graph, the average radar performance analysis is 4.1, which is doubles when we increase the temperature with the extended temperature workload as 8.6. So this is the performance analysis. From this we can say that even the respective of the temperature, whether it's been increased or decreased, the radar performed very well when compared to the other mechanisms. And the energy analysis. So here when you see the same thing, when you can see there is a difference between like when the 75% is considered and 100 is considered, 6.9 and 6.4, there's a very less amount of change we can see for the energy. This is because when the memory is been consuming constantly, the refreshes will doesn't occur fast. So doesn't require many refreshes. So that's the reason why the energy analysis is very less. I mean, there is no much difference between one mechanism to other mechanisms. Yeah, this is what the energy analysis results.
Will not take much time. In few minutes, we'll wind up, and let's have a question. So coming to strengths, like what strengths did you observe while we explaining in the radar? Any guesses? Okay, one. We are saving it for the end. Okay, let's go. And the first thing is like efficiency. Like it will reduce. It has already reduced 75% of the refreshes that has been doing before. And the second one is simplicity. In the whole presentation, we haven't mentioned any DRAM chip or anything that has been changed in the system. So it doesn't require like major modifications. It just only requires like memory controller changes only, that too like 1.25 KB of GB, 1.2 KB. So the next one is like compatibility. So I'll tell you a fact and you can remember this one, and at the end when we are asking the question, that might be helpful. This paper was presented in 2012, and yeah, that was presented in 2012. And coming to weaknesses, like the first step which we explained is profiling. So in the profiling step, we are calculating the retention times, but all DRAM cells, like some of the DRAM cells over the time, the retention times could be changed. But in this radar, only once we are calculating the retention times. So this is the one weakness. And the second one is like For example, a row has like many cells. At the starting example, we have seen only one bit has changed from 0 to 1 in 128 milliseconds. Because of that only one cell, we are going to refresh complete row. So that will be that is one of the weakness as well. And the key takeaways are like we have improved, RAIDR has improved 75% of the refreshes, like reduced, and it saved like lot of energy and time as well. And it doesn't require like many changes. It's like only changing the memory controller, that to like 1.225 KB. And thoughts and ideas, like the weakness I have told is like we are only calculating the retention time at once, like over the time it is going to change. So that thing, like the some other paper is there, like Avatar, like which is resolving this retention time calculation issue. And one more idea is like we can the second weakness I have mentioned is like because of one cell we are refreshing complete row. So that too, like we can reduce that as well, like by using half row refresh. For example, if we have a 16-bit array, we can split that to like left side and right side. We can see like which side we have like a weak cell, and we can in the Bloom filter, like we can store the row address plus whether it is left or right. So that is how we can use like half row refresh, and we can reduce some other like refreshes as well. So thank you for listening, and do you have like any questions? Feel free to ask. If you don't have any question, we will ask and we will distribute the donuts. Yeah. I guess he likes the donuts. Yeah, you can ask. It's just an idea. There was no like implementation part or something else. It's just an idea. Yeah. We are so by this idea we are dividing the row into two parts, left and right. If both the bits are from left side, we are going to only refresh the left one. If both the bits are from right side, we are going to refresh the right side only. If they are from like one from left and one from right, our idea is to refresh complete row. We can minimize some of the refreshes, right, by doing this. It's just an idea. There's no practical implementation yet. Yeah. Yes. Why would-
So the retention time is yes. I mean, come. Can you please come again with the question? I mean, because of the 64 base interval, we are reducing the reduction refresh with the retention time bin. That will reduce the power. Oh, yes. Yes, energy and everything. Yeah. Any other questions? This. Okay. Um, so instead of, so how the performance is been increasing is when we need to refresh that one, then only we are refreshing. We are reducing a lot of unnecessary refreshes, so that increases the performance. I mean, we are refreshing only when it is needed. We are not refreshing all the unnecessary bins, on all unnecessary rows refreshes. So that's how the refresh reduction reduces, and it improves the performance of the DRAM, because we are reducing all unnecessary refreshes.
Basically, when the processor access the request to the DRAM, so if the refresh rates, sorry. So if the refresh rates are more frequent, and if the banks are busy doing the refresh rates, it cannot serve the access request, right? So more frequent the refreshes are, more busy the banks are, and sometimes the bank parallelism may fail. So in order to get more hits, that means in order to serve more access requests from the processor, that can be done by decreasing the refresh rates, right? So more the access request hits, the performance increases, and also the energy and power consumption will also be decreased, because more refresh rates will be decreased and the access requests can be performed. Speed. So you mean the evaluation based upon? Yes, wait.
The graph.
It is
So
I.
it has been, the x-axis they have taken the memory intensive benchmarks against the weighted speed up.
So the base.
So benchmarks is like the intensity of the memory. Like if you are consuming 0% of the memory of a main memory controller, so how the results are going, and 25% of memory. And if you are using 100% of the memory consumption, and what are the results? So that's the work memory intensive benchmarks workload. It's like a CPU, as we have already done in here, in the benchmarks. So they have been taking spec CPU 2000, TPCC, and the TPCH as the CPU in order to test the real, how it is performing like a real DRAM. They have been tested against these workloads. Yeah, I hope I have answered this question. Yeah, thank you. And yeah, we have some few questions. So
So let me ask you a small question meanwhile. So I have mentioned, okay, what is the, like which generation DDR has been used to test this one, RAIDR? The, yeah, why? Why not 4 or why not 2? I have given already a hint. The paper was presented in 2012. Exactly. So at that time, DDR4 is not available and DDR3 is the version that is available.
Yeah.
Just for fun.
So these are all the questions. So
Yeah. What do you think about like false positives or negatives? Will it create like if we have more false positives, will it create negative impact? If we have like more false negatives, like which one creates more impact? Any one answer? Like both I'm hearing. So what is false positive first? When we say like false positive, what is the scenario that I explained? Yes, exactly. That's correct. So if we have is listening like uh, more. So if we have like more false positives, it doesn't affect anything. But if we have false negatives, we might miss some of the refreshes. So it can cause the issue. So that's
Okay, coming to the basic thing, how does a DRAM cell store a single bit of information? And we have the image on the board, like where the charge is. Capacitor. I don't know who answered the question to give the donut. What does retention time mean for a DRAM cell? Retention time. Okay. So when will you be refreshing the cell? Like time to refresh the cell based on what? Like up? Yes.
The last question for you, why did we
so if they use one function, if they have like more rows, if they insert like all the rows, like it get like collisions. If they use more hash functions also, like it might get like, if we are placing like 4 hash functions and if we are turning 4 zeros to ones, it might also gives collision. So that is why they have chosen the 3 hash functions. Like by testing with 2 and 4, they have selected the 3 ones, so it performed very well.
And one more thing is that, I mean, for each retention bin, we have a different hash functions like 10 and 6. So that means that it will differentiate between the entities or the rows to improve the error probability. So that's the reason why they have considered the hash functions.
And also they mentioned that the parameters can be based upon the capacity and also false positive, like how many do you want. So it doesn't affect the refresh rates.
All right, thank you so much, guys.
Thank you.
Let's cheer them. They a bit exceed the time, but let's move on. Make sure you send your voting. Okay. Can you attend online, or you'll be in another seminar, so you cannot? Okay, okay. Please send me email so you don't miss attendance. Do you have the microphone? Yeah, it's working. Be careful, don't click the button. Okay. Yesterday group, they mute themselves. by mistake. Right, whenever.
That's my phone.
Whenever you're ready, you can start.
Yeah. ಇಲ್ಲಿ ಏನೋ ಸ್ಲೈಡ್ ಅಂತ ನೆಂದಿನಂತ ಅದೇ ಅಲ್ಲ ಜರಗರಾಡ್ದು
Hello everyone, I'm Sanjana and my teammates are Saileenath and Bindhu. Today we are presenting the paper Efficient Memory Management for Large Language Models Serving with Paged Attention. This paper was published at ACM SOSP 23 conference which was held in Germany, and the authors are a team from UC Berkeley. Now, before we dive into the details, let me just give you a brief overview on what paper is about. So the problem is that GPU KV cache fragmentation, it limits throughput. It slows down large language models. The GPU memory gets filled up unevenly, wasting space and limiting how many tokens or requests we can process. So the authors proposed a solution for this, which is paged attention, inspired from paging technique in operating systems. And they have integrated this technique into a system and called it as VLLM. Because of this technique, they have achieved results 2 to 4 times more speed up and 96% memory utilization inside the GPU. This tells us that better KV cache management gives us higher throughput, which in turn leads to efficient reuse of memory management. Now, let's discuss what are LLMs. LLMs actually are AI models that are trained on huge amount of data to understand and generate human-like language. So what it does is it generates one token at a time depending on the previous tokens, right? For this, it uses a mechanism called attention mechanism, which consists of 3 main parameters. Those are queries, keys, and values. And all these 3 are stored inside the KV cache. You can see that in the diagram. Now, let me ask you a question. Have you ever noticed as we give longer inputs, it takes time to give the answer to us, right? Do you know the reason behind it? Does anyone know why it takes longer for the longer inputs? Yeah. Yeah. Answer is in the slide itself. Not directly though. Because of computation and memory management. Yeah. As the context gets longer, it takes too much of KV cache memory, and because of this memory management, it takes longer to give the output. Now, let's see how the LLM serving works. Means that how this ChatGPT and all these LLMs run in the real life. Like when we give a prompt and it gives us the output, right? There are 2 phases to this. First is prompt phase. Here, all the tokens are processed in the parallel inside the GPU at a time. So it is very fast and it is very efficient. Next is generation phase. It is also called as decode phase. It produces tokens one by one, each depending on the previous ones. So in the figure, you can see that for the prompt phase, all the boxes are moving together at a time. Whereas in the generation phase, only one box is moving forward, right? So the KV cache grows during generation phase and model becomes memory bound. So this GPU is limited not by compute speed, but more by memory that we discuss in future slides. Now, the rise of LLMs. Nowadays, we can see that we are using LLMs everywhere, right? Like chatbots, virtual assistants, content generation for coding help and whatnot. But because of how capable they have become, the demand for deploying them also have grown massively in the last year. But this comes with one challenge, that is cost. Now, a normal keyword search like a Google search costs only $0.01 per query, whereas an LLM search costs $0.10 per query, which is 10 times higher than the normal keyword search, right? What factors affect this cost is not just the computation, but also the KV cache memory. So to reduce this cost, we can use batching technique to help us improve the throughput, but this also helps only if the memory is used efficiently. Now, it tells us poor KV cache management leads to wasted memory and it leads to fewer concurrent requests, which in turn gives higher cost. GPU memory usage. Now, we have a diagram. It is a NVIDIA A140GB GPU, and here it shows how GPU memory is managed once the model is loaded. Now you can see the majority of the memory is taken up by parameters. These are the weights of the neural networks that are loaded, that are there once the model is loaded, and these are fixed. We can't change these parameters. Next, what we have is KV cache, and this is dynamic. It can grow and it can shrink. It depends on the tokens we get and the inputs we get. And others, it includes activations, or temporary computations, anything. So as we can't do much anything about parameters because it's fixed, and others activations and all, it's very small part of the memory. What we have to focus to manage memory efficiently is KV cache, and that is what this paper does. Now let's discuss what is KV cache. Does anyone know what is KV cache? Hmm? Yeah. Okay. In transformer models like GPT, every token generates 3 vectors, that is query, key, and value. During inference, the model uses these to figure out how much each new token is related to the previous token. So now let's understand what happens with KV cache and without KV cache. You can see the top part of the diagram that tells without KV cache. Whenever you need to compute the new token, that is token number 4, you need to recompute all previous tokens again, that is token 1, 2, 3. Because of this recomputation, the time for output takes longer, and also memory is managed inefficiently. Whereas with KV cache, you can see that whenever you need to process the new token 4, it does not recompute all the previous tokens again. Instead, it uses already stored key and value vectors in purple color boxes, you can see, right? It uses already stored values and gives us the output. It saves us so much time, and it also helps us manage the memory very efficiently. Now, let's discuss why existing systems fall short. Existing frameworks, what they do is they store KV cache in one big contiguous chunk. And because of this KV cache is dynamic, it grows and shrinks unpredictably. We can't tell how much length the user's request could be, right? It can be larger than the allocated memory. It can be smaller than the allocated memory. So it leads to an issue which is called fragmentation. And in this, we have 2 types, internal and external fragmentation. Now let's see this example. We have 2 requests, request A and request B. Now that request A, it consists of a sentence and it is allocated a big block of memory. That sentence is 7 years ago, our fathers brought forth, and that's it. Remaining, we have reserved space for that input, right? And that is internal fragmentation, because that blocks are allocated for this input, but the input is smaller than the allocated space. So we don't use that in future. So that memory just goes to waste. And between request A and request B, you can see there is small 2 gray boxes, right? It is too small to fit a new request, and we can't use that for any previous request as well. So this space also gets wasted, and this is called as external fragmentation because it is outside the request. And next, similarly for the request B as well, you can see there is reserved space at the end, which goes to waste. This limits memory reuse and reduces throughput and prevents concurrent sharing, this fragmentation issue. And in ORCA or faster transformer, only 20 to 38% of KV memory holds real token states. So because of this fragmentation issue, even the memory says that storage is full, but only 20 to 38% of that memory does have real token values, and remaining all is just wasted space. That is why we need to solve this issue, and that is what the paged attention mechanism does. Why not use existing methods? So people already tried to fix this memory bound issue, and now let's discuss what methods they have tried and what limitations those methods have. We have 4 methods here, and let's go through them one by one. First is static batching. Here what they do is they batch multiple requests of same input length together and process that request. It works only when the input lengths are same, but sometimes the inputs are smaller and sometimes are longer. So when the smaller request is done, it waits for the longer request to complete the process. So all this time the GPU sits idle and the memory gets wasted. So it wastes GPU slots when request end at different times. And next we have is tensor compaction. This method is used in ORCA model. What it does is it tries to fix fragmentation by copying active data into a new compacted tensor. It does reduce fragmentation, but the downside is that frequent copying back and forth increases lot of GPU cost and also GPU overhead. Next, what we have is static KV buffers. This method is implemented in faster transformer. Here, each request gets a fixed size buffer to avoid copying. That's good for simplicity. But if a request does not use all its allocated space, all the remaining space gets wasted. So it underutilizes the GPU. Next we have is DRAM or a unified memory load. Here what it does is it moves the KV data from CPU and GPU. Even though this expand the capacity of the memory, what it does is the PCIe transfers are very slow, and every time data moves between CPU and GPU, the latency increases and throughput drops. So let's see what the core problem is and why is it memory bound. So the KV cache growth causes ideal compute units, which means that GPU still has plenty of computation power, but because it does not have memory to store the new tokens, it does not compute any new requests. Next is that GPU memory bandwidth limits throughput. What memory bandwidth means is that how fast GPU can move in and out of the memory. It becomes the main issue. The GPU can do a lot of math, but it spends time waiting on data to arrive. So throughput or overall speed of serving drops. And this memory bound nature underutilizes GPU computation capacity. So what we need to do is efficient KV cache management becomes crucial to batch the multiple requests. Let's take a scenario. Here we have 3 chefs and only 1 counter. Even if the chefs are fast, they can't cook faster if there is only 1 counter space, right? Same thing happens. Even if GPUs have computation ability to do the task, if it does not have memory, it can't compute the task efficiently. So that's what our paper focuses on. Next, this is what the solution to that problem, memory bound problem. It is paging. You already learned about it, right? Does anyone know what is paging? It is there in operating systems. We use that. Yeah, correct. Now, here what we does is we adapt to operating systems paging technique and we develop a new mechanism. It is called as PagedAttention. Here it uses fixed size non-contiguous blocks instead of large allocations. It enables dynamic allocation as requests evolve, and it creates a logical to physical mapping for KV cache. Here in the diagram, you can see that you have a sentence, but it is not stored sequentially. It is stored in a non-contiguous blocks. 7 years ago, our fathers brought forth. It is divided into multiple blocks and stored. Even though here it shows it is not contiguous, when you look at it in logical sequence, it is a continuous allocation it has. So we use block table to map between the logical and physical sequences. Okay. Now let's discuss what VLLM architecture is. VLLM implements PagedAttention to manage GPU memory efficiently for LLM interface. It enables fast scalable serving by reusing cache data and minimizing memory fragmentation. This is the architecture of the VLLM. I'll just explain. First, what we have is front-end API. This is the user interface where users interact with it, user types in a prompt and everything. And next, it handles requests and parameters. Next, what we have is scheduler. It picks up a worker node and it gives the task to the worker node. The job of scheduler is to allocate the task to the worker nodes. Next, we have KV block manager. Here, what it does is cache engine and block allocator, they manage memory for the tokens. And the model shard you can see, right, that it runs computation using paged attention kernels, and it gathers KV by block table and updates in the cache. And next, oh, yeah. Okay. So finally, all these results are combined by the executor and runtime to generate the next token. Now my teammate will continue.
So why this architecture works? So the key reason this design works is because it separates a logical token order from physical memory placement. Physical memory placement. Next here you can see a block table keeps track of where each page of memory belongs. This allows data reuse, sharing, and preemption for all without copying data around. It also scales safely across multiple GPUs. Approach, this approach reaches about 96% GPU memory utilization, nearly with no waste. Now we'll explain how paging actually works inside VLLM, including memory scheduling, preemption, and multi-GPU scaling. So how paging works? So before going that, I will give you like an example. When you save photos on your phone and you try to access them in the albums, so they do not sit in the chip exactly by them in the same way, but yet you can open any album instantly. That exactly what logical versus physical mapping does here. Now let's see how paging works. Imagine that the tokens a model generates are arranged in logical order, 1, 2, 3, and so on. But instead of storing them next to each other in GPU memory, VLLM splits the memory into many small fixed pages. Block table records which physically page holds each token. A block table records which physical page holds each token. So even if the data is scattered, the model still sees it as one smooth sequence. So when a request finishes, it pages go back into global free list and can be reused.
I think you turned off the microphone. I think right there.
Okay, to conclude, this paper introduces the page detection algorithm that allows a large language model to store the key and value pairs in a non-contiguous page memory. The first thing, the takeaway is that they're designed in such a way that they achieve the near zero waste of the KV cache. And the second one is the flexible sharing of KV cache. This enables dynamic reuse of memory blocks such as parallel sampling and beam search. And finally, this VLLM is built on the page detection, which achieves 2 to 4% of high throughput with the same latency compared to the other models. Thank you.
Thank you, everyone. We are done explaining. And I think now we have achieved full GPU utilization and little bit of our brain utilization as well. Thank you for listening. If you have any doubts, you can ask us. Yeah. Questions అడుగుదామా మనమే? అడుగుదామా? Yeah.
You mean in the architecture?
Actually, we didn't even mention the words we are using in the slide. PagedAttention. They have already developed a model VLLM. They have already developed a model VLLM. We can install it through pip. But where we use it for the LLMs mostly to reduce the cache management.
I have a question. Why do you think they just combine the CUDA kernels into one operation, multiple operations into one operation? Why did they do that? CPU?
So can anyone say what is a tensor? You're almost there. It just stores the data. And can you say what's the difference between imperial tensor and a tensor? Imperial tensor and a tensor? Basically, imperial tensor is a temporary tensor. So it doesn't store the data. It's just just like a RAM. Just it'll be like a temporary thing.
Thank in the limitation. That to maintain back. Harder to maintain is that we just we just combining the page attention as well as dynamic scheduling. So maintaining this, compared to the general systems, the maintaining of this page attention and managing the smaller blocks and allocating the dynamic scheduling, maintaining the scheduling is harder compared to the basic systems. I'm just yes.
Overhead is because of the block table
Management.
just managing the block table operations.
And I just mentioned this this is a slight overhead. When it compared to the performance gain, this is very small. The overhead is just to maintain the memory management table. That's it. Times, go to the times.
I have a question. What is fragmentation? I already explained it. Fragmentation. There are two types, internal and external fragmentation. Not reuse. It's the yeah. The request is divided into blocks, but the fragmentation is the problem. Yeah. It's the wasted space of the request. Okay. How do they write it? So CUDA kernels is basically just combining a smaller things operations into one thing. Like usually in CPU we just compute one operation, but whereas in CUDA kernel multiple things can be thread. There are multiple threads actually that just combined into an that forms a CUDA kernel.
Can you answer that? Like how they implemented that. They just told they have combined all the. Yeah. No special driver
They
installations.
didn't mention about anything about that because they have patent operating on. Oh, yeah, but we can't. We need to get the access from them, but we can install it.
CUDA kernel is just a function that directly run onto the GPU.
How will you install it?
So that's the end of today. Thank you so much. We'll see you next week. But before that, we'll take attendance. So please send your opinion. You have about 1 minute. Don't have to say why, just nominate one of the two talks, which one is best. Please make sure you do it now. Oh, thank you. Thank you.
Yeah.
Thank you.